Hi, IBSL2. Tonight we are basically doing exactly what we did on 4.1 night. We're just talking about more rules of derivatives, but this time we're talking about derivatives of trig functions. So go ahead and label your paper. And there are a couple times throughout the video that you might want to pause and try a couple things on your own, and then push play when you're ready to check, all right? So 4.3 is all about derivatives of trig functions. And just to give you a little background, we are actually going to be doing more of this when we see you in class next time. But let's go ahead and do it for sine. So on your paper, we are going to go ahead and label 0. And then set your intervals because we're going to graph sine. All right? So set your intervals for pi over 2, pi, 3 pi over 2, and 2 pi. Just your basic 4 different intervals. So here's 2 pi. And then go ahead and take a minute to do the same. Okay? And then we have pi over 2 and 3 pi over 2. On the y-axis, of course, we know that sine is going to go up to 1, positive 1, and drop down to negative 1. So go ahead and label as best you can. And I will use black. Remember that sine starts at 0, 0. At pi over 2, sine is 1. At pi, sine is 0. At 3 pi over 2, sine is negative 1. And then at 2 pi, sine is 0 again. And then we want to make sure we have nice smooth curves as best we can. That one was a little far off. There we go. Okay, so there's my sine curve between 0 and 2 pi. What I would like to ask you guys to do is at each of our intervals, I want you guys to draw the tangent. So I'm going to use red for my tangent. Now, I know that my tangent at pi over 2 is going to be horizontal. I also know that my tangent at 3 pi over 2 is going to be horizontal. Okay. At 2 pi, it's going to be a diagonal as best I can. At 0, it's also going to be a diagonal. Okay. And then at pi, it's going to be a negative. All right. What I'd like you to think of is if I'm trying to take the derivative of sine, remember derivative, f prime, we're talking about the slope of our tangent lines. So again, slope of tangent. Let's just approximate what these slopes are. Okay? So my slope at 0 looks like it's positive. Let's just say it's positive 1. If I were a little bit more accurately drawn, it would look a little bit more like positive 1. At pi over 2, this is definitely a horizontal, so my slope is 0. At pi, it looks negative, so maybe negative 1. At 3 pi over 2, my slope looks like, slope of my tangent looks like it's 0 again, because it's a horizontal, just like at pi over 2. And then at 2 pi, it is positive again, so let's say that's positive 1. What I'm going to do is I'm going to map that onto a second graph. Okay? So a second graph, I'm going to use the x values that I had for my first graph, so I'm going to label the same way. I'm going to start with 0, and then I'm going to mark my pi over 2, pi, 3 pi over 2, and 2 pi. Okay? I'm also going to mark my y values at 1 and negative 1, same deal. And by finding the approximate values of the slope of my tangents, basically f prime, at the given x values, so at 0, at pi over 2, at pi, at 3 pi over 2, and at 2 pi, sketch the derivative. Okay? So my x values are going to be the same, but my y values, the points I'm going to graph here, are going to be the slopes of my tangent, which is what I'm asking you guys for here. So let's do that again in black. So at 0, the slope that I approximated was positive 1, right? So I'm going to put positive 1 here. At pi over 2, the slope that we were talking about of our horizontal was at 0. At pi, we said that our slope of our tangent line was negative, so we said that was approximately negative 1. At 3 pi over 2, the slope of our tangent line was back at 0. And then at 2 pi, the slope of our tangent line is positive again, and we'll say that that's approximately 1. So here's your ooh, ah moment. When we took the derivative of sine, what curve do we wind up getting? Right? So here we go. This is why when you take the derivative of sine, we get the cosine curve. Okay? Similarly, if you did the same thing with the cosine curve, we would get the rule for what the derivative of cosine is. So let's take a minute to write these up, and we're going to do a little bit more with these graphs when we see you guys next time. So we're going to make a little chart, and we're going to start with the three trig functions that we're going to work with most, which are sine, cosine, and tangent. The derivative of sine, as we just saw, is cosine. What winds up happening when you do the same type of graph for cosine, you get the negative sine graph. So it looks like sine, however, reflected over the x-axis. And then you have this tangent. Well, we're going to do a little work over on the side to show how we get the derivative for tangent. So first of all, we're going to write tangent as sine divided by cosine, because remember, that's one of your identities, is sine over cosine. Since I want to take the derivative of tangent, all right, I'm going to use the quotient rule. And I'm going to say the derivative of the numerator, so the derivative of sine, my new information tells me that is cosine, multiplied by my denominator, so multiplied by cosine, minus derivative of my denominator, so derivative of cosine is negative sine, okay, and then multiplied by my numerator, which is sine. All divided by my denominator squared. So cosine squared is cosine squared x. If I simplify this, I get cosine times cosine, so that is also cosine squared. Negative times a negative is plus. Sine times sine makes sine squared. And then divided by cosine squared. So let's think back to our identities. Oh, that wonderful word. Here we go. Cosine squared plus sine squared makes 1. And divided by cosine squared. Okay? 1 divided by cosine squared is the derivative of, what were we finding the derivative of? Tangent. Okay? So derivative of tangent is 1. I'm not going to be able to fit it in my box, so I'm going to write it a little bit larger. 1 divided by cosine squared, or you guys also know 1 divided by cosine squared as secant squared. Okay? So either way is fine, but the derivative of sine is cosine, derivative of cosine is negative sine, derivative of tangent is 1 divided by cosine squared or secant, but we do have to be familiar with both for future work that we'll be doing. So those are our three basic rules. So how does that change if we don't just have an x as our input? What if we have an actual function? So then the chain rule will apply. Remember, the chain rule says that we take the derivative of the outside function. So in this case, the outside function is our sine, our cosine, and our tangent. But then we keep the inside function the same, and then we multiply by the derivative of the inside function. So for sine of f of x, right? Similar to x, but for x our derivative is 1, so the chain rule doesn't really make a difference there. But for sine, derivative of the outside is cosine. We keep the inside function the same, so we'll keep whatever the inside function is. And then we wind up multiplying by the derivative of the inside function. So we multiply by f prime. This is going to work for all of them, the same exact way. So derivative of cosine is negative sine. Remember, keep the inside function the same. And then we are going to multiply by the derivative of the inside function, which is whatever the derivative is, which is f prime for now. So we're just representing it. And then tangent, again, you could use either one. So I could say, well, that would be secant squared of whatever the original function was, f of x, and then multiplied by f prime. Or I could wind up taking 1 over cosine squared of the original function. and then multiplying by the derivative. So multiplying by the derivative would wind up making the derivative my numerator. Okay? All of those are acceptable, but remember, this is really just the chain rule in action if you have something other than x, because x, the derivative is 1, so it really wouldn't make the difference if we use the chain rule for that. All right? Those are your new rules. So now we're just going to do a couple practice problems to make sure that they make sense. Again, pause the video here if you want to just make sure you have the two tables down and to make sure they make sense to you. For our practice problems, I'll do one of them first, and then again, my suggestion would be to pause the video, try the problem on your own, and then push play again and check to see how you did. All right, so for our first example, y prime, we have sine, and then x plus 1 is the domain of sine. It's inside our sine function. So this is a chain rule problem. I'm going to take the derivative of sine, which is cosine, keep the inside the same, which is x plus 1, and then multiply by the derivative of the inside. Well, the derivative of x plus 1, okay, is just 1. So that does not change it. So my derivative just winds up being cosine of x plus 1. Okay? Let's write that a little bit better. There we go. For the second one, we have two separate parts. We have the sine of x divided by 2, and then we have minus 3 cosine. So I'm going to treat them, because of this minus in the middle, it separates it into two separate terms. So I'm going to treat them as two separate terms. So first, I'm going to look at the sine of x divided by 2. Remember, guys, x divided by 2 is the same thing as 1/2 x. For some reason, this throws off students when they see it written a little differently. But x divided by 2 is just 1/2 times x, right? So 1/2 is really just a coefficient here. So when I'm taking the derivative of sine of x divided by 2, again, chain rule, the derivative of sine is cosine. I keep the inside the same, so I'm going to keep the x divided by 2. And then I want to multiply by the derivative of the inside. Well, the derivative of x over 2 is just 1/2. Okay? Minus, this 3 is a coefficient, so it's going to stay. Cosine of x, well, x is just, the derivative of x is just 1, so I don't really have to apply the chain rule here, even though I am technically. But the derivative of cosine is negative sine. And the reason why I'm putting it in parentheses is because those two negatives are going to cancel out, so I want to make sure I don't miss anything. All right, so let's clean this up a bit. It is appropriate to put our coefficients in front, so I'm going to put my 1/2 first, and then cosine of x divided by 2. All right, and then negative times negative, so that's going to make a positive 3, and then sine of x. Okay? Last but not least, let's try a tangent one. Derivative of 3 times tangent of pi x. So it is not just x inside of tangent. So I do have to apply the chain rule. 3 is a coefficient, so it stays. I'm going to use 1 over cosine for this one, cosine squared. Taking the derivative of tangent, keep the inside the same. So again, that's a common mistake there. Keep the inside the same. Well, my inside is pi x. So I want to make sure I keep pi x as the inside function. Okay? And then I want to multiply by the derivative of the inside function. Well, the derivative of pi x is pi. So how does this work? I'm going to simplify this down. 3 is in the numerator, 1 is in the numerator, and pi is in the numerator. So 3 times 1 times pi makes 3 pi. And then divided by cosine squared of pi x. Okay? When we see you in class next time, we are going to do a couple more problems. If you would like to get a head start, there we go. If you would like to get a head start, I'm going to leave these 4, 5, and 6 here. These are going to be part of your practice set when we see you next time. Have a good night.